Subtopic D of the 2018 call addresses the mid-term future in the planetary robotics realm. The next step in the exploration of the solar system will assume an enhancement of performance of the exploration probes. OG10 will implement subtopic D by prototyping exploration rovers that can take autonomous decisions on extended traverses. Today, autonomous rovers like ExoMars are expected to progress only a few tens of meters per day. This is insufficient to cover multiple geographic zones and get a scientific return of large diversity and value. Energy and locomotion are limiting factors, but the major constraint comes from the limited decisional autonomy. In future missions, it is foreseen that smarter rovers will traverse a few kilometers per day, increasing the scientific return of any mission while reducing the different resources needed for their operation. The main objective of OG10 is increasing the scientific return of future planetary exploration missions by developing higher decisional autonomy. This enhanced rover autonomy will be deployed along multiple axes. First, long-range navigation with higher reliability will be sought. Second, autonomous science will guarantee that significant scientific data along the traverse will not get undetected. Finally, autonomous resource management and safing will ensure that right decisions will be taken in presence of conflicting objectives. These objectives come along with several challenges. The first challenge concerns the capability to perform long traverses in the range of a few kilometers per sol. This implies that the rover shall be able to perform long-term planning and adapt the execution of the planned path with unprecedented speed and reliability. This adaptation includes path replanning when unpredicted events occur, such as the detection of natural hazards, rover resources limitations, or scientifically interesting targets. The next challenge addresses the maximization of the scientific return during these extensive rover displacements over the planetary surface. Taking images along the way and applying advanced image analysis techniques, the rover shall be able to detect peculiar environment features that could have a scientific interest and perform data collection in some opportunistic way. This may also imply the proper management of large volumes of data in presence of limited memory and bandwidth resources. The last challenge concerns the capability to manage in a reliable way the conflicting objectives of long-range navigation and opportunistic science in compliance with the safety, operational and resource constraints. This implies the development of an enhanced decision-making system featuring abstract reasoning as well as efficient planning and scheduling in the spatial and temporal domains. In addition, it involves the design of a thorough approach to qualify the autonomous system and validate the mission plans. OG10 will rely on most of the building blocks developed during the first phase of the SRC. SRECUS will be used as robotic operating system. ERGO will provide decision-making, planning and scheduling functionalities. The infused data fusion framework will constitute the smart perception core built upon the i3DS sensor suite. By assembling and tailoring these different bricks to address the planetary rover specifics, OG10 will develop a system that integrates the three main capabilities already mentioned: the long-range navigation, the opportunistic science and the autonomous decision-making that will arbitrate between roving and science. These capabilities will be finally demonstrated in some analog site environment. The demonstration will involve one sol-duration scenario with complete autonomy in order to be representative of Mars operations. An example of scenario can be: traverse at least a given distance in a specific direction under specific time and energy constraints and seize as many science opportunities as possible. Multiple variants will be considered with different formulations of objectives and constraints applicable to the long-range navigation and the science of opportunity. As far as the capability of opportunistic science is concerned, it will obviously rely for the most part on the detection of interesting features. However, to address the most general situations, the activity scope to be considered shall include a prior displacement to the target before performing data collection. The scenario is illustrated in the animation, where we can see the rover changing its course to approach interesting targets along a long traverse. Not all interesting targets can be evaluated in situ, as the required detour could endanger the achievement of the end goal in the sol. The demonstration shall involve a planetary rover with all the hardware and software components necessary to fulfill the objectives, a mock-up of the ground segment in charge of the mission plan preparation and rover telemetry analysis,